All right, so now we know that in order to write a quadratic equation or expression, excuse me, in Algeblocks as a perfect square, we need to create a square, right, with potentially some rods and some horizontal rods and vertical rods with the x square unit and then the ones. And we can have some loose units out there as well. So let's see if we can do that. Let's try this. So we have r squared plus 4r plus 4. Well, we have r squared and 4r. Well, if we want a square, then we better be breaking this up into equal amounts, like 2r and 2r. So if we want this to be a square, then we better have 2r here and 2r on that side. And if that's the case and we need a square, then the 4 will fill that in. So let's look at what we've got here. So we have the r squared, we have the 2r and the 2r, and we have the 4. So in fact, we don't have any loose. So we were able to place this quadratic expression into Algeblocks without having any loose values, any loose ones. So if we want to find what the factors are, we would have our r plus 2 on both sides. So the side of the square is r plus 2. Let me know when we meet next if you'd like me to show this with Algeblocks. All right, let's look at this one. C squared minus 6c plus 9. Let's see if we can set it up into a square and some loose ones. All right, so let's see what happens. C squared minus 6c. And again, we need to break those up into minus 3c and minus 3c if we want to make this look like a square. So here's minus 3c. Here's the other minus 3c, vertical and horizontal. And then we can have some loose ones, but let's see what we need to do to flesh out the square. Do you see that to line these things up, we need to have units in here. So actually what we have right now, let's see how that compares. The c squared, the minus 3c and the minus 3c. There's minus 3c and there's another minus 3c. And then we have this 9, which actually, plus 9, which actually is right here. So again, we don't need any loose ones because everything fit nicely into a square. And the square is c minus 3 in size. So it's c minus 3 all squared. So take some time before you go on and look at B and D and try to do that yourself. But we'll do E and G together. So things don't always work out as nicely as they did for the first set of examples. So let's take a look at h squared plus 6h plus 3. Again, we're looking at something that's going to look like that. So a square and then some loose ones. So let's see what's going to happen with the square. That's h squared. Now plus 6h, those would better split evenly. All right, so it's 3h and 3h. And then we have plus 3. That is not enough for us to complete that square. We need more. We need, in fact, 6 more here to complete that square, right? But we can't just be going around adding 6 units to the positive side of any mat. We need to make sure that if we are doing that, that we do it as part of a zero pair so that we don't change the value. So now we do have it in form that we have a square and some loose ones. So what's the size of the squares? So the size is h plus 3, right? And it is a complete square. And then we have a minus 6. Minus 6. And that's our completed the square form. All right. I'll let you do F as well on your own, but we'll do G together. So we are still looking for something squared plus some loose ones, right? A square and some loose ones. Now, but here we have minus r squared. So let's see how that's going to play out. The 6r has to split into equal because otherwise we wouldn't have a square. We're lining everything up. And then in here, we have -9. And in fact, the -9 is exactly what we need. So it just so happens that what we're given actually does fit into a perfect square. So we won't need the loose ends. But let's see if we can figure out what the factors are, or what the sides of the square are. Well, on the horizontal, we have -r plus 3. And on the vertical, we have +r minus 3. So we have -r plus 3 times r minus 3. Well, notice that the distance, the actual length, is exactly the same. It's just they're opposites of each other, right? Where the r is positive in the vertical, it's negative on the horizontal. Where the 3's are negative in the vertical, they're positive in the horizontal. So it's as if we're, instead of squaring 2, we're multiplying 2 by -2. And what do we get? Isn't that -2 squared, or -4? And what if we did 5 times -5? Isn't that -5 squared, or -25? Right, so wouldn't this be r minus 3, but the negative of that square? So what does that mean for our function? Right, we do have a square, so it's a right shift of 3. But what does this negative mean? Right, do you remember that it means reflect down? Right, so that's all it is. It's a function that's pointing down, that's opening up downwards. All right, so I'll ask you to do F as well. Now, we're not going to be talking about the examples with the coefficient in front of the square term at this point. There is a way to use Algeblocks. In fact, in general, what we do is we would factor out the 2. And then factor what's inside, and then put the 2, and then bring the 2 back in. But we're not going to go there this time around. If you're interested, I'm happy to record some videos for you of that as well. So J we'll do together. So minus y squared plus 6y plus 2. So again, we need something squared plus something. So minus y squared plus 6y. Looks very familiar, very similar to the one we just did. And then plus 2. So there's plus 2 in here. Interesting. Those plus 2 can't really fit into our square. What we really need in our square are these 9. Right? These -9 to make that square. Well, if we're going to have -9, or if we're going to add -9, those better be part of 0 pairs. Otherwise, we're going to be changing the value. So let's see what we have now. So we do have a square, and that one is -y plus 3 and +y minus 3. Right, so that's that same situation that we had before. It's kind of like 2 times -2. All right, they're the opposites of each other. And then plus, and on the plus side we have 11 loose ones. So That's how we would complete the square here. Now, if we're looking for interpreting this, this means that it'll open downward. This means that this value will be 0 at y equals 3. So right shift by 3. And this means up shift by 11. Right? So our vertex, this point that would normally be 0, 0, would actually be at 3, 11. Okay. Now let's take a quick look at these questions. So what do you have to do to change a quadratic function into a vertex? So I would like you to write out what we just did in order to get something like this. What does that look like? What does the square look like? Right? What does that square look like? Maybe these are the x squareds, and these are the rods, right? And these are, whoops, these are the x squareds, and these are the rods, and then these would be the singles, right? So, and then there'll be some loose ones. So I'd like you to write out in your own words what you have to do in order to be able to get to that form. Now, why do you think it's a vertex form is a good other name for it? Right? Remember when we had minus y minus 3 squared plus 11 just earlier? And we said the vertex is going to be shifted right by 3 and up by 11. So let's look at what's going to happen here. 1, 2, 3. So instead of the function looking like this with a 0, 0 vertex, it's actually going to have the vertex. The vertex is going to be at 3, 11, and it's going to open downward. So why do you think this form can be called the vertex form? Based on the information that it provides. So take your time to write that out so that you have it for your notes when you're studying or when you're using Algeblocks in the future. Now let's take a look at what now happens if we don't have the Algeblocks, right? So we could have been drawing all of those, using all Algeblocks for all of those things that we've just done up to now, but what happens if we don't? We certainly can draw what's going to happen, as I have been in this particular lesson. But let's say we have x squared plus 5x plus 5 other x, right? So, and then here we have 9. So we have we have 9, but we don't have enough. We still need this one, and we need all of these. Okay, we need all of those. Right? But we can't be doing that. We can't just be going around and saying, hey, that's 26. I'm just going to add 26 extra. Because what's going to happen is, oh, it's not 26, it's 25 total, so 16 extra, pardon me. So I can't just be going around and adding 16 extra. I need to make sure that those are part of 0 pairs. So let's see if we can find the factored form or the vertex form. It's x plus 5 squared, right? This, we took half of the x's to be on the horizontal and half of the x's to be on the vertical. So this becomes x plus 5. And then minus 16, because those are the pieces that ended up being loose at the end of it all. So there we go. Now, this works really well with large numbers so that you don't actually have to draw them out. But it also does a really good job with numbers where you might have a difficult time splitting things in two. So for example, if you have x squared plus 5x plus 3, you might have a tough time figuring out how to split 5 rods into equal parts, right? Equal groups. So let's see if we can draw them out though using the Algeblocks. So if we have x squared, and then here we're going to split this up in our minds into 2.5 x's. All right, so this would be x plus 2.5, and this would be x plus 2.5. We couldn't do this on the actual Algeblocks, but that's what these would be vertical, and these would be horizontal, however they're lying. But there'd be 2.5 of them. So then, here, 3 pieces would not be enough. Sure, we'd have 3 pieces, but what we actually need to fill this out, right, is 2.5 times 2.5. Do you see that? It's a square. That's 2.5 times 2.5, or 5 halves times 5 halves, which is 25 quarters, or 6 1/4. 6 1/4. But we only have 2 or 3 of them in there, right? So we need to be adding another 3 1/4. So more 3 1/4. But we can't go around adding 3 1/4. We'd need to make sure that that's part of a 0 pair. So let's write this out now. We have a square that's x plus 2.5 squared minus 3 1/4. And if we want to use fractions, we can write it this way. Okay. So what I'd like you to do is work on D, to see if you can use the idea of Algeblocks to solve this, the visual of Algeblocks, to write that as a vertex, in vertex form.